Okay, welcome to another fabulous day in Calculus 3. We're going to do the chain rule today. And I'm really excited because in the whole entire semester, this theorem, the chain rule for functions of several variables, is one of the key theorems in the whole semester. So you can brag about that when you get done with the course, okay? And there's a couple other theorems that we're going to learn coming up, in the next couple months that are equally important, but this one's a biggie, chain rule. So first, let's do a quick recap. What did we do last time? Last time we did something called partial derivatives. The name is misleading because we didn't do anything partially. They just call it partial derivatives. So if you recall, if you have a function of two variables, x and y, so you got x here, you got y here, you're going to have two first partial derivatives. So one of them can be denoted f subscript x. That's the derivative of f with respect to x. And you would hold y constant and take derivative with respect to x. The other first partial, we using subscript notation, f subscript y means take the first partial of f with respect to y. So then you treat x as a constant. Okay, and then we had some other notation that you want to be comfortable and familiar with. So this differential notation here, df, oops, that's supposed should be df dy. This is with the melted d's. So the curvy stem d's is how we denote partial derivatives. And that's making the distinction between a curvy stem d and a straight stem d. Know the difference because we're going to be working with both. And you have to know the difference between these notation wise, otherwise you lose points. Okay. So we are going to do the chain rule. So let's go ahead and review a quick Calc 1 look at chain rule. So when did you use the chain rule in Calc 1? When did it come into play? Typically, it came into play when you have what was known as a composite function, a function that sort of had an outside layer and an inside layer. So an example where if you were going to take the derivative, you would need the chain rule would be this function, y is equal to x squared plus 7 to the 5th power. Let's take the derivative for fun. So if you recall, if we were going to go y prime, you would first take the derivative of the outer layer, and you would use the power rule here, 5x squared plus 7 to the 4th times, this is why they call it the chain rule, you're chaining, the derivative of what's inside parentheses, the derivative of x squared plus 7, and that is 2x. And then, of course, you'd want to clean this up because you want to multiply the 5 and the 2x together, make it look kind of pretty, and you're done. And so there is the chain rule in action. Now, what actually is going on here? When you use the chain rule in Calc 1, when they taught it to you, most likely they taught it to you in the following way. They said, well, if y is equal to f of x, then df dx, which is a way to say f prime, you would first take df du and multiply that by du dx. And that's why they call the chain rule. Well, what about who's the u in this example here? So here we had u was x squared plus 7. Okay, and so f of u was u to the 5th power if we treated the x squared plus 7 as u. And so then when we did df dx, we first did df du, which is 5u to the 4th, times du dx, which was the 2x, and then we back substitute for u to finish it off. What did we call u in the first place? Well, for this little problem, we called it x squared plus 7. So then you would substitute the x squared plus 7 in there, and then you would then finish it off and make it look pretty by multiplying the 5 and the 2x together, and you'd be done. So this right here is the key. That's the key. So I want to draw you a little tree diagram for that because we're going to be looking at tree diagrams today, and I'm a tree kind of girl, so it helps. So you start at the top, you've got your y is equal to a function of x, but you can rewrite it as f of u. And so then what you have to do, since this function is a function of u, but u is a function of x. Okay, so you kind of have this tree thing going on. So on this branch, you would first take the f du, and for us that was the power rule. And then to get from u down to x, we had to take du dx. And then when you multiply these together, these branches of your tree, you get df du times du dx. Okay, and that's sort of the mini tree that you had in Calculus 1, although they may not have drawn any tree diagrams for you. Okay, fine. So we're done with the review. Now it's time for Calculus 3 and the chain rule. And there's two biggie cases for the chain rule here in our class. So the big two cases, and we'll do one at a time. So the first one we're going to look at is when you have w is a function of x and y, say, well, it could be more, where x and y are functions of a different variable. They're functions of a single variable, and that's what this is the first case. And we're going to call that variable t, although it doesn't have to be named t. You could use a different letter. Okay, that's the first case, and we're going to look at that first. The second case, so the second portion of this chain rule lecture, we're going to look at w again and have it still be a function of x and y. So that hasn't changed. Where x and y themselves are functions of two variables. Maybe even more, but we'll keep it easy for now. And let's name those variables with some letters, say u and v. So let's do the first one, case 1, where you have a function of a single variable driving the bus. Okay, so case 1 theorem, chain rule for one independent variable. That would be the letter T for that first little case. So let w be a function of x and y. So we use that notation f parentheses x comma y, where f is a differentiable function of x and y. Now, if x is a function of t, and let's say we say he's g of t, and y is also a function of t, say h of t, and g and h are differentiable functions of t, then w is a differentiable function of t. So that means you can actually find w prime of t. And we'll use the differential notation here, dw dt would be, and be very careful here because I'm going to be having different styles of the letter D here in this formula. And yes, it matters because you're going to be writing this out on your handwritten work. You're going to go dw dx, and that's a partial derivative, so use the curvy stem d, but you're going to multiply dw dx by dx dt, where since x is a function of a single variable, you're going to use the straight stem d to denote his derivative. Plus, we're not done, dw dy, that's a partial derivative, so use the curvy d, times dy dt, that's straight stem d. Now, if this looks kind of scary, don't worry, it's going to all be clear soon. Write it down. Now, the schematic, and when I say schematic, that's going to be a tree diagram. The schematic that the textbook uses is going to look like the following. So you've got w at the top of your tree, and w is a function of x and y. So then you have the tree growing out there. And then x is a function of t, and y is a function of t. And that's how the textbook does it. I don't like that. When I do my tree diagrams, I do it where I think it makes more sense, and I'll show you what I mean. I got w at the top of the tree. W is a function of x and y. And x and y are functions of t, but it's the same t. Like this t that you see down here with these two separate bubbles, the way the textbook does it, these are really the same guy. It's not like this t over on the left is a different t than the one over on the right, but it kind of looks that way, the way that diagram is written. So the way I sketch it is x and y are functions of t, and they're sharing the t. And t is the driver of the bus, because whatever he does, whatever he changes to, since he can affect x and y, and then x and y themselves can affect w at the top, t can drive the bus. And so this is the schematic that I prefer. Now, if you like the book's way, I'm okay with it. Just know that when they have these separate T bubbles at the bottom of the tree, that T is really the same T. Don't forget. That's why I like mine better. Okay. Let's do an example of the chain rule. Okay, so, well, hang on. Let me finish my tree. I'm sorry. I want to finish my tree. So what do I need? So how does this tree, or either of these trees, relate to this formula? So you start at the top, and notice dw dx, which is a partial, goes first. And so you go down this tree branch, dw dx, w connecting x, and then you multiply that by straight stem d dx dt. And that gives you the first term. Plus, you go from w down to y, and you do that by taking the partial of w with respect to y. And then you multiply that by dw dt right here. And that gives you that second term. So the tree can help you understand this formula better. And that's why I think tree diagramming is great. Okay, now we'll do the example. All right, there's two ways to do a chain rule example that's kind of basic, where you can kind of do what I call cheating. The first method, we are going to, in fact, use the chain rule for functions of several variables. In other words, we're going to use this theorem up here and get an answer. The second method is we're going to use substitution, and that's going to circumvent using the chain rule altogether. So it's kind of cheating, but I mean, you still get the same answer. But if you were doing that on a quiz where the instructions were use the chain rule and you use method 2, well, I'm afraid you're going to get 0 credit because you did not follow the instructions. So let's look at both methods, shall we? So here we have w at the top. W is in fact a function of x and y, because you can tell there's x's and y's in there, x squared y minus y squared. And x is equal to sine t, so he's definitely a function of t. And y is equal to e to the t, so y is also a function of t, and they're both the same t there. They want us to find the derivative of w with respect to t. T is typically time, but it doesn't have to be. So fine, here they're saying time, it is time. Time is equal to 0.
So the answer is 2xy cosine t.
Okay, Lupe, I'm going to stop you right there. So by the theorem, it says that dw dt, and notice this is straight stem d, is going to equal the partial of w with respect to x. You're going to come down this tree branch, and you're going to multiply that by dx dt, go down that tree branch, and then you're going to add to that, you're going to flow down dw dy, so that's a partial, so make sure you use your curvy stems for the d, times dy dt. And then you complete all the branches of your tree. So I'm going to do the components of this big old formula, because notice you need 4 derivatives just to finish it. So let's do each of the 4 derivatives separately, and then we'll substitute it back into this big old chain rule formula. Okay, so separately, what do we have? Let's get dw dx. Let's get the partial of w with respect to x. So if you look at w here, it's x squared y minus y squared, fine. You're going to put on that special set of glasses that I told you about, where you hold y constant and just treat y as if it were a pure number, like the number 3, for example. So the derivative of x squared y with respect to x would be what? Just tell me that, Lupe.
Wait, I'm sorry. What
The
did you ask again?
derivative of just the x
Oh,
squared
yes, it's
y.
2xy.
Perfect. Thank you. Minus, and then while I've got you on the line there, Lupe, what is the derivative of minus y squared with respect to x?
The are you talking about the derivative of that and
Just
with
the minus y
yes, it's zero.
squared with
It's
respect to
zero.
x.
Yes.
It is?
Yes.
What is it?
0.
Good. Okay, perfect. So I don't even need to write the minus 0, so I'll just erase it. Perfect, thank you. Okay, now let's get the other partial. Let's get the dw dy. So since it's a partial, use these curvy stems for the d's. So now you're going to put on a different set of glasses. Woo! And you're going to hold x as constant. And you're going to take the partial of w all over again, but now with respect to y. So the partial of x squared y with respect to y would be x squared minus the partial of y squared with respect to y. That's easy peasy, just 2y. Okay, we got two down and 2 to go. We got our partials. Now we need the other 2 ingredients. We need the derivatives of x and y with respect to t. So let's go do that up here. What is dx dt? Use a straight stem d because this is a function of a single variable, just t. So if x is equal to sine of t, I think everybody knows what the derivative of sine t would be. It's cos t. And then let's get the other derivative. This is not a partial, so use a straight stem d. The derivative of e to the t with respect to t is e to the t. Okay, we have all 4 ingredients, so let's put it all together in this big old formula. So the dw dt, straight stem, is 2xy, and then dx dt was cosine t, plus dw dy was, in parentheses matter, so please put parentheses around the quantity x squared minus 2y, times dy dt is e to the t. Okay, bad news. I'm not going to give you credit for this, and neither is MyLab Math. Wait, what? We did all this work for nothing? Oh, man, that sucks. Well, here's the deal. When you're taking dw dt, since t is the driver of the bus, I only want to see the variable t in your final answer. I don't want to see x's and y's and t's. I only want to see t. Oh, so what do? Well, you notice that they're giving you x and y in terms of t. So you're gonna do some back substituting. What do you mean? Well, this 2xy, in place of x, you're gonna put what x is in terms of t, which is sine t, because they told us. And then the y, remember, was e to the t, and then you still have the factor of cosine in there. Let me copy it down before I forget. Plus, and then this second term here, make sure you do all your substitutions. So x squared for us is going to be sine squared t minus 2y is 2e to the t. And let's clean this mess up a little bit. Well, yeah, just leave it. I could clean it up. I'm gonna, they did tell me just evaluate it at t equals 0. So I'll skip the cleanup since they just want dwt at a certain value. So I want to do this notation. So vertical bar, and at the bottom put t equals 0. This is standard notation. And so what am I going to do? We're going to substitute t equals 0 everywhere we see a t, and then hopefully this comes out to some interesting number. E to the 0 is 1, remember, and sine of 0 is 0. So since sine of 0 is 0, that whole first term is gone. Plus, this is going to be 0 minus 2 times 1 times 1, and then I get a final answer of -2. So the change of w with respect to time t is -2, and I'm done with part A. Whew, that took a while. So you got to have some patience. If you're the kind of person, well, if I don't have the answer in 26 seconds, I'm out. Well, these problems are going to take a little bit longer than that. So let's do method 2. So method 2, we're going to basically do this problem all over again, and we're going to get the same answer. It's like, but we're going to use a different approach. We're going to use a different approach. So what does that mean? We're going to circumvent using the chain rule altogether. So how is that done? So the way we're going to start with method 2 is look at your W and notice you got X's and Y's in there. Let's do the substitution right now. So in other words, everywhere you see X's, you'll substitute sine t. And then everywhere you see a Y, you'll substitute e to the t. And then W will just be a function of t. So if they want dw dt, we'll just, use all our knowledge of taking derivatives for, from Calc 1, and we'll be done. So I need some room. So here's our W right now. It's x squared y minus y squared. So we're going to use method 2 here. We're going to just substitute. So your W is going to be sine t squared times y, but that's e to the t, minus y squared. And I'm going to rewrite this so it's a little bit prettier. I'm going to put the exponential in front of the trig because that's common. That's more standard. And keep in mind, I do appreciate when you follow standards in your work. And e to the t squared is just e to the 2t. So now let's take the derivative of this, dw dt, just using your Calc 1 knowledge. I hope that you can see that this first term is going to require the product rule and the chain rule at the same time. What do you mean? Because this sine squared, I'm going to rewrite it as sine squared because it'll actually be easier for me to get my mind around. So your dw dt is going to be, first take the derivative of the first factor. Well, the derivative of e to the t is e to the t. And multiply that by the second factor, plus now take the derivative of the second factor. Okay, you got to use the chain rule. 2 sine t to the 1 times the derivative of sine t, that's cos. And there we have the derivative of that first term, minus the last guy, but the derivative of e to the 2t using exponential rule from Calc 1 is just e to the 2t times 2. And if I evaluate this guy at t equals 0, I hope I get the same thing. And I should. Because sine of 0 is 0. So this is gone. Sine of 0 is 0. That's gone. This is minus 2 times 1, which is negative 2. So it is the same. And that's circumventing the chain rule. So if you're a thinking student, you're probably thinking, well, why do I even care about this chain rule? Like, she just showed us a way where we cheat and don't even use the chain rule and just use our calculus 1 skills. Why do I bother? Because a lot of the problems that are going to be given to you, you will not have cheating capability. And we're going to see those in today's lecture. You won't be able to circumvent it using this cute little trick. Yeah. So get behind learning that powerful chain rule because it's going to hit you. All right. So I'm going to do one big old example next, and then you're going to try one. Are you ready? You're going to do example 3, but not yet. Let me do example 2. Okay. So this example 2 is a perfect example where you won't be able to cheat. This won't be possible. Can't cheat it. So how are you going to work it? Well, first read it because it's going to be a word problem. And yeah, there will be word problems on this week's quiz. So just read it. A rectangular block of ice. Okay. With length L, with W and height H is melting. Oh, I'm melting. When the length is 9 feet, the width is 8 feet, and the height is 2 feet, these variables are changing so that dl dt, the change of the length with respect to time, is -1 foot per hour, as it melts, it's shrinking. The change of the width is -2 feet per hour, and the changing of the height is -1/3 foot per hour. So this poor little rectangular block of ice is shrinking, shrinking, shrinking. So what do they want? Letter A, what is the rate of change in the volume of this melting, shrinking block of ice? Give units in your answer to get full credit. Ooh. Where do we even begin? Don't worry. It's going to be pretty straightforward. First, what is your function that you're even doing business with? Well, it turns out we're working with volume, and volume is a function of 3 variables. Oh yeah, length, width, and height. And in fact, volume is just length times width times height. Okay, here's the function we're going to do business with. Okay. Now, if you're a thinking person and you liked my tree diagrams, I highly recommend before you do a problem, draw a tree diagram. So there's volume, and we got length, and we got width, and we got height. It's a function of 3 variables. Uh-oh, can we do that? Sure. Because all 3 of these variables, length, width, and height, are all functions of time t. The same t. So if we were to come up with the change of volume with respect to time using our tree diagram, you first go down this branch and you're going to take the partial of volume with respect to L, the length, dV, dL, and you're going to multiply that by this branch, which is the derivative of length with respect to time. And that's a straight stem D because L is just a function of a single variable. Single variable derivatives are straight stem. Plus, then you go down this branch, which means you're going to have to take the partial of V with respect to W, okay, curvy D's, times dW dt, the derivative of width with respect to time, or the rate of change of width with respect to time, plus, and then this last big old branch here, take the partial of volume with respect to height, and multiply that by the change of height with respect to time. And there's your formula. And to get full credit on my quizzes and exams, before you start plugging stuff in and doing stuff, if I don't see this critical initial step, you will lose points, a lot of them, because I don't like you just plugging willy-nilly into something, a formula you have in your head, but you're not showing on your handwritten work. That's key. And that's making a legitimate mathematical argument for something. So now what? Oh, holy cow. How many derivatives total do I need to make this cake? Look at all these ingredients. 1, 2, 3, 4, 5, 6. Holy smokes, I need 6 derivatives to do this one problem. Now, they gave you dLdt, dWt, and dHdt. So you don't even have to go get those. So you can, right where it says dLdt, put -1 foot per hour right here. And then, so no derivative needs there because they just gave you the value at that snapshot time. The dW dt, the change of width with respect to time, was -2 feet per hour. Okay, -2 feet per hour. And then the dH dt, the changing height with respect to time, -1/3 foot per hour. Okay, great. But I still got to go get those 3 other derivatives. Yes, we do. But it's not that hard. Like, take a look. We've got our volume, which is length times width times height. It's a function of 3 variables. What would dV dL be? So put on your special glasses, and hold the W and the H constant. Pretend W and H are like the number 3. I don't care. All right. What would be the derivative of LWH with respect to L?
WH.
Good. How about dV dW? So put on a different set of glasses now. You're taking the partial with respect to W, only this time you're going to hold L and H constant. So dV dW would be?
LH.
And then how about last but not least, dV dH? New set of glasses. You want to keep the L and the W constant.
LW?
So you've got your 3 partials right there, and so you're just going to substitute those here. Okay. So dV dL, and by the way, I want to see each and every one of these intermediate steps on your exam paper. Like, don't skip step and go, oh, I did this in my head and I immediately did direct sub with, numbers. I want to see the blood, the sweat, and the tears. Okay? I don't see them, no full credit. Now what? Well, you're almost done. But what's missing now, you want to get what is the changing volume with respect to time. Everywhere you see a W, an L, and an H, you plug in what the word problem told you that those values are. Not the dW dt and dH dt. Those are changed. Those are rates. They said length is 9, width is 8, and height is 2 at the exact moment we were trying to figure out the changing volume with respect to time. So you want to plug those in. So down here, you're going to go, okay, 8 times 2 times, and these are feet, right? Feet, -1 foot per hour, plus, and then L times H. So you got 9 feet, gotta go too fast. Hey, erase tool. Hang on. Recalculating. 9 feet. Whew. Okay. 2 feet, and then -2 feet per hour, plus LW 9 feet times 8 feet times -1/3 foot per hour. And so what I want you to see here is the units. Because look at each of these terms. You notice you have feet times feet times feet per hour. You're going to get an overall feet cubed per hour because that is what dV dt is going to be. Volume is feet cubed for this problem, and the time element we're using here is hour. And then you just, punch this up in the calculator and add it all together. I get -16 minus 36 minus, what the heck, 24. And I get -76 cubic feet per hour. And we're done with this problem. And that is the changing volume with respect to time. And it seems like that block of ice is shrinking pretty rapidly. Losing volume fast. So what was the whole point? You couldn't do this problem without the chain rule. You need it. Okay. And you probably did something like this when you took Calc 1. I don't know if you remember related rates in Calculus 1. This is very similar. So letter B, a few years back, I gave letter A in lecture, and then I gave letter B on a quiz, and then half the class did not do so well. And they complained that they didn't know what surface area was. That's why they couldn't do the problem. Oh, gee. So I decided just to put the surface area one in my lecture. That doesn't mean I won't put it on a quiz. You should still be ready. What is the surface area of a rectangular box? I mean, if you look at all the sides of the box and add up all of those areas, that'll give you overall surface area. So I'm going to call it S, and you'll get 2 times what? Width times height. So if you looked at the width times the height, that'd give you the front face of the box. And this will be the length here. And there's 2 of them, a front cap and a back cap, plus 2LH, so that'd be the top and the bottom, plus 2WL, well, I guess WL would be the top and the bottom, 2LH would be more sides. Okay, so there's your surface area function. And this is a function of length, width, and height. It is. So if we do the tree diagram again, you're gonna have that. So your ds dt is going to be take the partial of S, the surface area, with respect to L, and multiply that by dl dt, plus go down another branch, take the partial of S with respect to W. This is going to be a little bit harder, okay, than part A. Yes, with respect to W, and then multiply that by the straight stem derivative dw dt. Oops, that's a plus, not an equal. Sorry, too fast. Plus, and then the last big old tree branch here. Take the partial of S with respect to H, and then multiply that by dH dt. Okay, so we got all the ingredients. There's 6 derivatives again, But keep in mind, we already have the LDT, DWT, and DHDT because they gave us those actual rates. At this moment, they want us to find the changing of the surface area. So what we need to get are the partials. So this is a little bit tricky because this function is not as straightforward as the volume formula. So let's take a look here. So let me repeat. Here's our surface area function, 2WH plus 2LH plus 2WL. When you're doing ds dl, for example, you're going to hold the W and the H constant and then take derivatives with respect to L. So this is going to end up being 0 because there's no L's in there. This one will be 2H and this one will be 2W. So ds dl just ends up being 2H plus 2W. Fine. How about ds dw? So you're going to take the derivative, partial derivative, with respect to width. You're going to hold L and H constant. So the derivative of the first term, 2WH, will be 2H. The second term, 0, because there's no factors of W. And the last term, 2L. And then finally, ds dH, you're going to hold L and W constant. So you're going to end up with 2W plus 2L. Okay, so then your ds dt, when you put this all together, is going to look like, okay, 2H plus 2W times dl dt. And yes, I like to see all these intermediate steps. I don't know why people protest so much about writing everything out. Now, there's some of you, I must say, your handwriting is gorgeous, and I wish I could write as neatly as you. When you do your handwritten work, it's like a work of art. You put all your steps in there, and it's just beautiful. I love that. You could give a workshop on doing good handwritten work. And now the plug-in begins. You already have these rates of change for length, width, and height. That was -1 foot per hour, -2 feet per hour, and -1/3 foot per hour, respectively. And then the H, or the length was 9 feet, the width was 8 feet, and the height was 2 feet. At this exact moment, they want the changing surface area. So I'm going to factor out a 2 here. I'll go 2 plus 8 times -1 plus 2 times 2 plus 9. Whoops. Here, this was -2 feet per hour. And I'm being a little bit cavalier here because there are units. But the units are going to be what? So remember, you've got feet per hour with all of these rates. And here you have feet, 2 plus 8 feet. This is feet, this is feet. So your overall units are going to be feet squared per hour, not feet cubed, because surface area is not feet cubed. So this is going to end up being, after you punch this up in the old calculator, I got -226 square feet per hour. Okay, that's the changing surface area. Whew. I know, right? Yeah. So this is the chain rule in action. I'd like you guys to have a chance to try one. So you're going to be doing example 3 for me. Resume the report. Did anybody get the answer letter D?
Yeah.
Yes.
Okay, I hope you did, because that was the answer. If you didn't, let's go in slow-mo here. What's going on? If you draw a tree, I always like my trees. The surface area is a function of only 2 variables, R and H, and R and H themselves are functions of time, T. And if you do the ds dt formula, if you go down one tree, you're going to take the partial of S with respect to R, so ds dr, times dr dt, so you write that down, plus, then you go down this branch, which is the partial of S with respect to H, ds dh, and you multiply that by the derivative of H with respect to time, dh dt. So notice I have curvy stem and straight stem, letter D's both. But the good news is this one's a little bit easier than the last example because we only have 4 derivatives total to go get. And they already told me what dRdt is. They said that the radius is increasing at a rate of 9 inches per minute. And then the height is decreasing, so negative 7 inches per minute. So those are two derivatives or rates that I don't need to go get. But I do need to get those partials. So you got to be careful here. dsdr, if you look at this formula for surface area and you take the derivative with respect to r, oof, you're going to hold h constant. The derivative of 2 pi r squared, I believe, is 4 pi r, plus the derivative of 2 pi rh with respect to r is 2 pi h. And then the other partial, ds dh, so now you're going to differentiate with respect to h, hold r constant. The derivative of 2 pi r squared with respect to h is 0 because there's no factors of h in there. And the derivative of 2 pi rh with respect to h is 2 pi r. So this is just going to be 2 pi r. Okay? So then when you put this all together into, big mess here, you're going to have, ds dt is going to be, this 4 pi r plus 2 pi h times the 9 inches per minute plus 2 pi r multiplied by negative 7 inches per minute. Now, what about the r and the h? What goes there? Well, they told you that at the moment they wanted that change of surface area, the radius was 12 inches and the height was 32. So you're just going to put 12 in place of the r's and 32 in place of all the h's, and then multiply it out and watch your units here. So you'll get 840 pi square inches per minute. And that's the answer. And you're done. Congratulations if you got it right. If not, hopefully it was just a silly mistake and you can clean it all up. Let's do the next case. So we're done with first case for chain rule. Case 2, this one's harder. What if you have functions with more than 2 independent variables? So before we had one independent variable, time t. T was the driver of the bus. Now you may have more than one driver of the bus. So in this example, w is a function of x and y, and x is a function of 2 variables, g, u, v. Y is another function of 2 variables, h, u, v, such that all of those first partials exist. Then you're going to have 2 partials to worry about, dw, du, and then dw, dv. So we're going to have 2 formulas here. Oh yeah, it's going to get messy. So the partial of w with respect to u is going to go dw dx times dx du plus dw dy times dy du. And all of the letter d's have curvy stems in this particular formula. No straight stems at all. The partial of w with respect to v, look at all these curvy d's here, is going to be dw dx times dx dv plus dw dy times dy dv. Now, it looks like with these 2 formulas, it looks like we have 8 derivatives total, but we actually don't, because both of these partials have something in common. They both have dw dx, and both of them have dw dy. So it turns out there's 6 distinct partials that you have to go get when you do both of those formulas. Let's look at the schematic, okay? So the textbook and me differ. So I'll show you what the textbook shows you. You got w, it's a function of x and y, and x is a function of u and v, and y is also a function of u and v. Okay, that works. That's how your textbook rolls. So I prefer a tree diagram that's really more accurate. So w is still a function of x and y, but x and y, which are both functions of u and v, are functions of the same u and v. There's not like, 2 different u's and 2 different v's, which it kind of looks like from the textbook diagram. My tree diagram shows a more accurate picture that u and v are the drivers of the bus. Those are the 2 independent variables that are driving the entire bus. Okay, if they change, then x and y change, and then that changes w. Okay. So if you use this tree, either of these tree diagrams to get these formulas, dw du, you first go down the dw dx, and you want the derivative with respect to u, so you go down the dx du. So that gives you that. Plus, you got to go dw dy, and then you go down dy du right there. Now, what if you need the other partial of w? I'll use green. So you still have to go down dw dx, but then you go down this branch and get dx dv. Okay? And then you still have to go down the dw dy branch, but then you want the partial with respect to v. So you go down this branch, dw dv. Okay? That's tracing out your tree diagram. So let's do an example, and then we'll do a really hard example. And all of these are going to show up in your homework and quizzes. So like I don't just like take these out and go, oh, here you go, I'll torture you with this. You'll see it. So this one, they want both partials, dw du and dw dv. And w is a function of x and y, and x and y are both functions of w. So this tree diagram here, or this one, is both of those apply to example 4, okay? Okay, so let's get these in turn. So if we're going to get the dw du, I'm going to write this out. You got to go get dw dx and then multiply that by dx du. I'm doing this one first, plus dw dy times dy du. So let's do all of that. I need to get 4 derivatives total. Oh my goodness. So let's get all 4. So look at w. What would dw dx be? That's a partial with respect to x. That means you're going to hold y constant. So sine of y also just looks like a constant multiple, you know. Hey, a constant multiple times e to the x, the derivative of that is just the constant multiple times the derivative of e to the x, but e to the x derivative is e to the x. That was easy. So we got that. What about dw dy? What would that look like? So look at w all over again, and now try to differentiate that guy with respect to y. So you're holding x constant. So that means e to the x just looks like a constant multiple. So e to the x times the derivative of sine with respect to y, and that's just cos of y. So there's 2 of the 4 derivatives that we need to go worry about. Now let's get the other 2. Here's x and here's y. What would dx du look like? Well, if you take the derivative of uv squared, with respect to u, you're holding v constant, and so that's just going to look like v squared. And then dy du, the partial of y with respect to u, I believe is going to be 2uv. When you put this all together, there's a little bit of bad news here. We had something like this. So your dw du is going to look like dw dx, you've got e to the x sine y, times dx du, that was the v squared, plus dw dy, that was e to the x cos y, times dy du. So I hope you can appreciate that MyMathLab will not accept this as a final answer for your dw du. Why not? Because u and v are the drivers of the bus. Those are the only 2 variables you're allowed to see in your final answers. But I'm looking here at this answer. I got x's, y's, u's, and v's. It's a hot mess. So you need to do some replacements. Everywhere you see the x, and I see x happening in the e to the x, you need to substitute uv squared. And everywhere you see a y, substitute u squared v. So when I finish this up to make it look the way it's supposed to, and I'm kind of purposely doing some stuff here, I'll use a different color. So you're going to go e to the x, but x is uv squared, and sine of y, but y is u squared v. And you're pretty much done, but I would really appreciate it if you follow the mathematical custom, and any coefficients and polynomial factors should go in front. So right there, it'd be nice if you move the v squared in front of the exponential like that. And then here, bring the 2uv in front, just because that's tradition. And it looks much prettier and easier to read. So there's a dw du. Boy, what a hot mess. And you could factor out a common factor, whatever. I'm not gonna, just leave it. Now, what about the other partial? Because they wanted two and we only got one. Oh man, you're kidding. No, go get the other one. Okay. So now you're going to get the other formula. So they want this partial of w with respect to u. So you know, you got to go get dw at dx, excuse me, that's dw dv. We already got dw du, dx dv plus dw dy times dy dv. Now, good news, we already got the w dx and dx dy. Those are done. So this one was e to the x sine y, and this dw dy was e to the x cos y. So we already got those guys. So we just have to get these other partials with respect to y. So dx dv, but x was equal to uv squared. So if we take the derivative of uv squared with respect to v, we'll get 2uv, and dy dv, what is y again? I forget. Okay, y is u squared times v. The derivative of that with respect to v, holding u constant, is just u squared. And remember, you can't leave your answer with all these different alphabet letters in there. It's a mess. You want to clean it up and replace the x and y with what they told you. So this answer, and I'm going to start making it look pretty, put the 2uv in front. You got e to the uv squared sine of u squared v plus u squared e to the uv squared cos of u squared v. Okay, and there's your other partial. Oh my. That is pretty gross, but it's very formulaic. It's just you doing a lot of partials. So you need to know your partial derivatives cold to do this section. So how can it get worse? Well, some of the examples that aren't in Briggs, but they're in other textbooks, and I love other textbooks the way they do this, and you'll see something like this. Suppose you're given z, which is a function of x, y, and x and y are themselves functions of two variables, s and t. This gets really alphabetically complicated, but they're just trying to trick you. They're giving each of the variables a different name. Do you have a nickname? You probably do. You know, maybe your friends call you something else, or maybe your family has a nickname for you. I don't know. So you respond to different names. And that's kind of the idea of this problem. So here z is the function, but he also responds to being called f. He got a nickname. And he's a function of x and y. But x and y have nicknames. What do you mean? X can also be referred to as g, and g is a function of s and t. And y has a nickname. He could be referred to as h. He's a function of h. Now, s and t are the drivers of the bus. So there's a picture. That's a tree diagram. Now they're telling you when s and t, those are the drivers of the bus, are the values 2 and -1, you have some values for all of these other guys and some of the partials that go with it. So they're telling you the g function itself is 3, but gs is some other number. That's the subscript notation. That's the partial of g with respect to s. gt, partial of g with respect to t, is some number. H is given something, and then h is partials, okay? And then they give you partials for f. Oh my God, what a nightmare. What do they want? They want the derivative of the parent function z with respect to s. That's one of the drivers of the bus. And they want the other partial with respect to t. So let's write these out, and then we'll put in the nicknames. So dz ds, if you're following this tree diagram, you first have to go down this branch, which is dz dx. All these are partials. And then you multiply that by dx ds down here. Plus, then using this tree diagram, help you out, you're going to go down this branch. You're going to go dz dy times dy dt. okay? But because X and Y and Z all have nicknames or different names, we're going to rewrite this formula with the nicknames they get, the different notation. Z, his name is F, so you could in a sense be thinking, okay, they wanted DF, DS, but I'll leave that as DZ, DS because they did. But DZ, DX, since, excuse me, that should be, yeah, DZ, DX, what is that? That is F, X, because I'm taking Z, whose name is F, and I'm partially differentiating him with respect to X. So that's the same. DX, DS has another name because X is referred to as G. That's G subscript S. Take the partial of G with respect to S. And then DZ, DY, we can call that FY. And DY, DT, we can call that H. And I screwed up here. I apologize. This should be, you guys didn't say anything. Aha! I was testing you. Since we're taking the derivative with respect to S, this should be dy ds. My bad, sorry. Dy ds. And so that's going to be HS. Okay, now why did I change all these up? Like, who cares? Well, because they gave us values for all these at the specific point. So fx at the required point is 12. So you're going to go, oh, that's a 12. And then GS, the partial of G with respect to S, they told us it was a 5. Oh, cool. Plus FY at the point was a 7. All right. And then HS was a 2. Okay. All right. What's 12 times 5 plus 7 times 2? I get 60 plus 14. I get 74. Bingo. That's one of the answers. That's the partial of Z with respect to S. Didn't even have to take any derivatives. Ha ha! But I did have to know my tree diagram. What about the other partial? We need to go get dz dt, which is dz dx times dx dt plus dz dy times dy dt. Okay, but those guys all have duplicate names. So if you go and use the nicknames, if you will, and replace, you're really saying dz dt is going to be fx times g subscript t plus fy times h subscript t. So this is going to look like 12 negative 3 plus 7 times negative 2. I get negative 36 plus negative 14, and I get negative 50. And we're done with this problem. So what's the point? The point is very cool. And that is, look, you didn't have to do any partials here, but the powerful chain rule is used. And so if you know your chain rule, you're going to be fine. And if you get that some of these functions are going by other names, you're fine. Now, I put a MyLab math problem into my lecture notes here. That's right. I just did a screenshot of it. Check this out. Use a tree diagram to write the chain rule formula for dy dc, where y, oh my God, is a function of 3 variables, r, s, and t. Okay. And r looks like it's a function of 1 variable, g of c. S is a function of 2 variables, b and c. And t is a function of 3 variables, a, b, c. And so here are all your choices for tree diagrams. So will you be able to pick the right one? What I do is I draw my own and then, try to see, what's going on. So I know that y is the same as f because they're giving it 2 names. And it's a function of 3 variables, r, s, and t. So start drawing your bubbles. But r is a function of only 1 variable, c. So he's just going to go down here. S looks like his other name is h, fine. He's a function of 2 variables, b and c. And then the last guy, t, is a function of 3 variables, a, b, and c. And you're pretty much done with a tree diagram. The question is, do any of their choices match my drawing. What do you guys think? You have to be really careful because they're also putting this in the branches.
Would it be the bottom right?
Mm-hmm. Mm-hmm. Yeah, and so this one is correct. Why is that one correct? But letter C, which sort of has the same look, is not correct. Does anybody see why letter C is not okay? It's very subtle.
The dt over dy on the,
Yeah, this is upside down. It's upside down notation. That should be the derivative of y with respect to c, and they accidentally wrote it, or drd, excuse me, with respect to r, dy dr, not dr over dy. So they were doing upside down partial differentiation notation. So this one had bad notation along the branches of the tree, and this one was cool, dy dr, that looks good, and this is drdc, and so on and so forth. So this one's the good one, and we picked one. What about the chain rule? Like, if they wanted the partial of y with respect to c, that's their ultimate goal. So using the tree diagram, if it helps, which one of these choices is the correct partial of y with respect to c? Ooh, gosh, look at all those choices. My goodness. So if you follow the correct way, if you look at the tree, dy dc is going to be, you're first going to go down dy dr and then times dr dc. Plus, then you're going to go down the dy ds branch, and then, oops, not ds, you got to go to the c because you're always going to c. ds dc. Plus, then you're going to go dy dt, and then t's got to go to his c, so times dt dc. Now, folks, to be honest, if I were to draw that tree, I would have drawn it like this, just because how I roll. Down at the bottom, you would have 3 drivers of the bus. You would have the drivers of the bus be A, B, and C. R is a function of C only, so his branch goes over there. S is a function of B and C, and T is a function of A, B, and C. Although my tree does look kind of messy, but I claim it's more accurate because you only have a single A, a single B, and a single C driving the entire bus. Okay. So here is the answer. Which one of the choices that they gave here looks like it's going to be a match? And there was one answer I did wrong. I'll tell you why. This should be a straight stem D for the R. Why straight stem? Anybody want to guess?
I'm gonna go for it. I think it's B.
Okay, B is correct. Congratulations. So notice DRDC is straight stem, and it should be. And the reason why is what? R is a
Straight
function
sum.
of one guy. See how when you have a function of a single variable, that's the one time you'll use straight stem D's for your derivative notation. If somebody is a function of 2 or more variables, you start using curvy stems because that's when you start getting into partials. Okay. So letter B is correct, and that is the correct chain rule formula. Letter C, good God, that's a hot mess. Forget that. Letter A is not okay because this DC-DR should have been DR-DC. That was a big baddie. Letter C is just a hot mess. Forget that. This one, no, you don't need 3 factors here to get down, to drill down into your C. That's too much. Okay, that doesn't mean you'll never do it. If you had a 3-layer tree you would need terms that had 3 factors to drill down your tree, okay? So I think this is probably a good place to quit, which means that next lecture, I'm gonna go long. Yeah. All right, congratulations.